Hey guys, I'm John and welcome to Respect Your Intellect. It came to my attention that there are a lot of misconceptions and misunderstandings when it comes to the Big Bang, so we'll be talking about that today. So in this video, we'll cover the history of how the Big Bang was discovered, the other early theories that were discarded in favor of the Big Bang theory, we'll address some of the biggest misconceptions and misunderstandings about the Big Bang, and we'll talk about the 4 pillars of evidence that we have that support the Big Bang. We'll also cover the 5 main periods of the expansion of the universe. Let's get started. There will be a few things about light in this video, so if you haven't seen my video on light yet, you should definitely go check that out first to understand everything in this video. I'll leave a link in the description, or you can check it out right here and come back afterward. Let's start with a bit of history about the discovery of the Big Bang. It all starts in 1922 when Alexander Friedmann predicted a universal expansion of the universe using Einstein's general relativity. A bit later in 1927, Georges Lemaître was the first to propose that the expanding universe could be traced back to a single point. This is because if we measure at different intervals and record the movements of objects, we can then extrapolate their movements and positions backward through time. Then in 1929, Edwin Hubble made the first direct observations of the expanding universe when he recorded the redshift of distant objects and realized that there was a correlation between distance and redshift. This led him to develop Hubble's law that states that the further an object is, the faster it's moving away from us. Hubble's law only has 2 possible explanations. Either we're at the center of an explosion of galaxies, or the universe is uniformly expanding everywhere. The former goes against the Copernican principle that states that humans, Earth, or our solar system are not privileged observers of the universe. Hubble's law became the cornerstone of the Big Bang theory. After that, in 1948, Ralph Alpher and Robert Herman predicted that there would be a cosmic microwave background radiation left over from the Big Bang. And finally, in 1964, Arno, Penzias, and Robert Wilson discovered the cosmic background radiation and were awarded the Nobel Prize in Physics in 1978. When the Big Bang theory was first conceived, it was contending with another theory called the steady-state theory. The steady-state theory was a model that theorized that the density in an expanding universe stayed proportional due to a continuous creation of matter. This theory is now rejected by the vast majority of cosmologists, astrophysicists, and astronomers. This is because the observational evidence that we call the 4 pillars of the Big Bang all point to a hot Big Bang event with a universe of a finite age, while the steady-state theory makes no such predictions. Now let's talk about the misconceptions and misunderstandings about the Big Bang. Contrary to what its name suggests, the Big Bang is not an explosion in space, but rather an expansion of space. A lot of people just tend to call it an explosion because it avoids having to go into a tangent to explain the expansion of space, but that's ultimately incorrect. Another misconception is that the Big Bang is the creation of matter from nothing, but this is very far from what the Big Bang theory claims. When the universe was very young, it was a very different place, much hotter, much more dense, and much smaller. All the matter we can observe today was already there at the beginning of the universe, and a lot of it even annihilated each other to leave us with only a small fraction of the matter. So the Big Bang theory actually predicts that we lost the majority of the universe's matter rather than the popular belief of the Big Bang having created matter. Alright, now that we got the misconceptions out of the way, let's talk about the evidence we have for the Big Bang. When it comes to evidence for the Big Bang, we have 4 main points that we call the 4 pillars of the Big Bang theory. The first pillar is Hubble's law that states that the farther an object is, the faster it's moving away from us. Hubble's law can be observed directly by looking at various distant objects like galaxies. What it does is support the claim that space is expanding uniformly from everywhere. The second pillar is the discovery and measurement of the cosmic microwave background radiation. This background radiation was theorized to be visible from anywhere you look at in space, and that it would be the remnant of the Big Bang. Arno, Penzias, and Robert Wilson were the first to detect it in 1964, and they were awarded the Nobel Prize in Physics for it in 1978. Since then, we had better and better maps made of it with the WMAP spacecraft, and this map is in agreement with the large-scale structures we can directly observe in space today. The third pillar is the abundance of light elements in the universe. This is not light as in photons, but light as in very little mass like helium, deuterium, lithium, and a few others. Everything else in the universe was created much later inside of stars during their evolution or when stars exploded as supernovae. This is also directly observable and correlates well with the predictions made from what we know about the Big Bang. And the fourth pillar comes from more recent observational evidence of galaxy formations and evolution, as well as the distribution of large-scale cosmic structures. Our observations and simulations show that the first quasars and galaxies formed when the universe was only about 1 billion years old. Quasars are essentially extremely luminous black holes that can be thousands of times brighter than our entire Milky Way galaxy. This is because the gas around them releases insane amounts of electromagnetic radiation as it falls towards the black hole. Since those first quasars and galaxies formed, larger structures like galaxy clusters and superclusters have continued to form. This is also all in agreement with our simulations based on the information we have. In 2011, we also found pristine clouds of primordial gas by analyzing the absorption lines of the spectra of distant quasars. This was the first time that we found clouds of gas with no elements heavier than hydrogen and deuterium, which means that those clouds were likely formed in the first few minutes after the Big Bang. On top of these four pillars, our estimate of a 13.8 billion year old universe is now in agreement between the Hubble expansion, the cosmic microwave background, and the oldest stars. As for the future, we're hoping we can add a fifth pillar by detecting gravitational waves from the very early universe. This would give us a direct observation of something that occurred less than 1 second after the Big Bang, giving us a glimpse at what we're having trouble seeing right now. So now that we know we have strong evidence that all agree with each other, let's talk about the timeline of the Big Bang itself, as well as what we know and what's still up for speculation. The first period is what we call the singularity. We don't have much information about it just yet, so this period is still open to a lot of speculation. It's essentially the point at which everything converges to an infinitely dense and infinitely hot universe when we use general relativity to extrapolate backwards. This suggests that our current laws of physics are insufficient to explain this early period of the universe. Perhaps in the future we'll be able to unify general relativity and quantum mechanics under a quantum gravity theory that will yield more answers, but we're not there yet. The main problem with general relativity is that it resides in classical physics, while the other three fundamental forces are described in quantum mechanics. Unfortunately, we can't consistently combine classical physics with quantum mechanics, and that presents a substantial problem in our quest to understand the very early universe. The second period is what we call inflation and baryogenesis. This entire period takes place when the universe was only an extremely small fraction of a second old, so it's too early and different for us to explain everything at this point. What we believe happened in this period is that the very small universe was uniformly dense and experienced very rapid heating and cooling temperature fluctuations. During this period, a phase transition happened that caused a cosmic inflation and the universe grew exponentially. This growth left ripples of varying densities which became the large-scale structures we see today, like clusters of galaxies. When the inflation stopped, the universe reheated and was able to produce the first elementary particles. The temperature of the universe at this point was so high that everything in the universe was moving at just under the speed of light. All this energy caused particles and antiparticles to continuously be created and destroyed in collisions. Then we believe something happened that we call baryogenesis. This baryogenesis event would be responsible for violating the conservation of the baryon number, which is just a fancy way of saying the total value of particles in a system in quantum mechanics. What this led to was an excess of matter over antimatter by about 1 part in 30 million, and resulted in the predominance of matter that we see today in the universe. The next period is called the cooling period. Everything before this point happened in a tiny fraction of a second, but when the universe becomes 1 second old, things start to slow down significantly. There's much less speculation at this point because we can directly observe these conditions in large particle accelerators. During this period, the universe continued to decrease in temperature and density, so the particles in it were less and less energized. This is the period in which the fundamental forces of physics came into existence in the form that we observe them today. This is also the time where the elementary particles formed that will later become atoms. This period also includes a mass annihilation event between matter and antimatter, and left the universe with no more antimatter and only 1/10 billionths of the matter it previously had. The same mass annihilation event also happened between electrons and positrons when the universe was about 1 second old. After this mass annihilation, everything slowed down and the universe was left with light as its main source of energy. At about 379,000 years old, electrons and atomic nuclei combined to form the first atoms, which were mostly hydrogen. At this point, radiation decoupled from matter and became known as the cosmic microwave background radiation, which is one of the pillars of the Big Bang theory. We can actually see the cosmic microwave background radiation from when the universe was about 400,000 years old, and it's considered the best observable evidence that confirms the Big Bang. We also think that during this period, when the universe was 10 to 17 million years old, there may have been a habitable epoch that contributed to the chemistry of life. The next period is what we call structure formation. During this period, the universe was still pretty uniformly distributed, but there were slightly denser regions and slightly less dense regions. The slightly denser regions started attracting nearby matter by gravity and continued to grow denser. This resulted in the formation of gas clouds, stars, galaxies, and other structures that we can observe today. We actually have a map of this from the cosmic microwave background, and it allows us to perform real measurements and observations about the early universe. The spacecraft that imaged it was operating from 2001 to 2010, and it was called Wilkinson Microwave Anisotropy Probe, or WMAP for short. And finally, we have the last period, which is called cosmic acceleration. We believe that space is infused with dark energy that's responsible for space accelerating its expansion. When the universe was much smaller and denser, gravity was able to dominate over dark matter and acted like a braking mechanism to slow the expansion of space. As space continued to expand, gravity had less and less effect in the universe as a whole and became overpowered by dark matter. This means that as the universe continues to expand, it also continues to accelerate as well. So to conclude, the four pillars of the Big Bang, as well as a few other observable pieces of evidence, are the reason why it's the predominant model today. It wasn't just a choice we made because we liked the idea. It's a conclusion that was drawn from many observations that all agree with each other and seem to only be explained by a Big Bang event. Since the Big Bang is not an event that suggests creation from nothing, it doesn't require a belief like many people think. We have a lot of evidence that supports it, and we're able to trace it back to very near the beginning. We still need to figure out parts of the very early periods that we can't yet observe directly, but that doesn't invalidate all the other evidence that we can observe and are in agreement. We currently have a lot of studies and experimentation happening right now for these periods, as well as dark matter and dark energy that we don't have much information on as of yet. Hopefully, each advancement in those fields will help us explain more and more of the events of the Big Bang. If you found this video helpful, please hit that like button. If you want more, hit the subscribe button and the notification bell if you want to be notified of new uploads. Feel free to also share this video or tag someone that you think could get value from it. You can also find links in the description for my Twitter and Facebook if you want to interact with me on social media. Until next time, thanks for watching, and remember, respect your intellect.